Okay, to practice, how about take the following, try this perhaps on your own. Take the vector field, so let f be the vector field x times y times z, comma x squared times y squared times z squared, comma x cubed times y cubed times z cubed. Okay, take this vector field and find the divergence of this vector field. Why not pause for a moment, try it on your own, and then see what you get. Okay, I hope you really did that. If you then unpause, the divergence needs to be a scalar. So it should be partial derivative of the first component with respect to x. And we should get yz for that, plus partial derivative of the second component with respect to y. So we should get 2x squared yz squared for that, plus we should take the partial derivative of the third component with respect to z and end up getting 3x cubed y cubed z squared for that. Just keep in mind that you really do need to get a scalar. If you ended up with a vector, you drew commas in your answer, something went wrong. Let's try another one. Let's let f be the following vector field. So angle bracket. We'll just use different notation here. Why not? How about x to the fourth z minus 3z squared, okay, times the vector I, plus quantity y minus 4x cubed yz times the vector j, plus quantity y minus z times the vector k. So it's just written in IJK form instead of in the angle bracket component form. And then find the divergence of this vector field. Give this a video pause, try it on your own, see what you get. Okay, so let's go ahead and compute the divergence. Again, we need to get a scalar field, so don't write angle brackets here. That would be incorrect. We need to take the partial derivative of the first term with respect to x, and we'll get for that 4x cubed z, and then the second term, negative 3z squared, is just going to differentiate to 0. Okay, then the next component, the j component, we need to differentiate with respect to y, and we'll get 1 minus 4x cubed z, plus finally the third component, y minus z, we need to differentiate that with respect to z, and we're going to get, well, 1 minus, differentiate with respect to z, so 0 minus, we'll get a minus 1 for that. Again, what we have is a scalar. Let's clean up this scalar a little bit. You'll notice 4x cubed z cancels with 4x cubed z, and we have a plus 1 and a minus 1. We actually end up, folks, with the scalar 0 for this. Now, I want to recall that just a little earlier today, this vector field here, x to the fourth z minus 3z squared I, plus quantity y minus 4x cubed yz j, plus quantity y minus z k, this was actually the result of taking a curl. This was the curl of the following vector field from earlier: 2x plus yz, comma x y squared plus z cubed, comma x to the fourth yz. So go take a look at that. Maybe pause the video again, see that in your notes. Now the point is that there's a theorem that, again, we're not going to prove, but we actually just saw an example of it, and it looks like this. For all vector fields, for any vector field, let's say for any vector field f, capital F arrow, well, we just have seen an example of divergence of curl of the vector field is actually always going to equal the 0 scalar. So this kind of mimics what we saw earlier. We earlier saw a theorem which was curl of gradient of f is 0. Now we have divergence of curl of f is equal to 0. For appropriate f, though, it's gotta work. We won't say a lot about. Well, we'll see why this theorem is important a little later. But for now, I just would like to point out some connections. So we saw the curl of gradient. Now we could draw the upside down triangle thingy. I'm just going to actually write out the word grad this time. Okay, curl of gradient of a scalar field, lowercase f, was equal to the 0 vector. and the theorem that we just cited here, divergence of curl of a vector field, any vector field, is equal to the zero scalar. These are related to some really truly other areas of math we're not going to dig into, but I think it's just a neat factoid to point out that this is related to something in algebraic topology. Specifically, even in there's a related or a sub-subject area called homology, or homological algebra. Chain complexes. This area of math goes by lots of names. I'm just trying to give you some of the buzzwords. And if you're just curious, you want to kind of look up these in the context of some of these areas just on the web, feel free, but don't worry about it for this class specifically.